Okay, welcome to section 3.6. Here we're going to talk about implicit differentiation. So this is yet another technique for differentiating relations, functions, and the like. All right, so let's consider what I have right here. The equation y equal to f of x, and then right next to it, we have this relation f of xy equal to a constant. Now, up to this point, many of the functions or relations that we were differentiating were all of this form, y equal to f of x. So an example would be, right, like y is equal to 3x squared minus 5, okay? So here y is a function of x, and this is what we would call explicit form. Okay, so an equation that's written in explicit form is an equation that looks like this. Y is a function of x. But I could have written the equation like this, the very same one. I could have written it as minus 6x squared plus 2y is equal to negative 10. Okay, so notice the expression on the left-hand side of the equation is an expression in terms of x and y, and on the right side is a constant. Okay, this is what we would call implicit form. Okay, so in fact, if you're of this form, we would write y is an implicit, so y is an implicit function of x. Okay, or another way you could say this is f is determined, so f is determined implicitly, okay, so implicitly by the equation. Okay, so again, that's two ways you can describe this relation that we have here. Y is an implicit function of x, or f is determined implicitly by the equation. Okay, now what I want to do is something like this. Okay, so here's again my minus 6x squared. And since y is an implicit function of x, okay, I'm going to go ahead and replace the y with f of x. Okay, because y is an implicit function of x, so I replace it with f of x. And then notice what I get, minus 6x squared plus 2 times. Now, what is f of x? F of x is what? 3x squared minus 5, right? So 2 times 3x squared minus 5 is equal to negative 10. Okay, and then from here, I get minus 6x squared plus 6x squared minus 10 is equal to minus 10. And then what do you notice here, right? We notice that we have what? An identity. Okay, that's exactly what we have here, right? This is an identity. Okay, so what does that mean? It means that this equation that we have right here is going to hold for all values of x. All right, so let me say this. F is implicit if and only if substitution of f of x for y leads to an identity. Okay? So f is implicit if and only if substitution of f of x for y leads to an identity. All right? Okay, now, in this example, how many different functions are determined implicitly by the equation x squared plus y squared is equal to 1, right? So if I substitute for y a function and it leads to an identity, well then that function is implicit, right? Okay. All right, so how could we do this? Well, I can take my equation x squared plus y squared equal to 1 and I could solve for y, right? So in other words, y squared is equal to 1 minus x squared. So y is equal to plus or minus the square root of 1 minus x squared. So in other words, I was able to produce what? A function, two functions here. One function f is the square root of 1 minus x squared. And then the other function here, g, is the square root of minus 1 minus x squared. So in other words, f and g are determined implicitly by the equation. Because if I substitute either function into this equation here, what do you get? You get an identity. Okay? In fact, the reason why I have the picture of a circle here, in fact, we're going to call this the unit circle. Okay, right? So this is going to be the unit circle here. And if you take a, let me color code this for you, but if you take a look at function f right here, right? Function f is the upper branch to this unit circle. And then we'll put this in, let's say, green. The function g here represents the lower branch to the circle. Okay? So the graph of each function determined implicitly by x squared plus y squared is equal to 1 is a portion of the graph of the unit circle. Okay? Make sense? Now, I could have also taken or constructed another function if I wanted. I could have, let's say, constructed the function h of x, and I'll do it piecewise. So h of x is made up of the square root of 1 minus x squared, and then minus the square root of 1 minus x squared, where the top function is going to range from -1 to a, and then the bottom function is going to range from a to 1. Okay, and so if I construct a function in this fashion, well, then the equation is also determined implicitly by this function. Okay, in fact, if we were to take a look at the graph of this guy, it would look something like this. Here's -1, and you would have one piece doing this, where this is a right here, and then you would have another piece, let's say, doing something like this. Okay, if you could see that, right? Okay, but this function here would be determined implicitly by that equation. Okay, so these are the functions that are implicit. And that's because, again, if you take these functions and substitute it into your equation, the equation being x squared plus y squared is equal to 1, then you get an identity. Okay? Okay. So now let's go and take a look at this example here. So suppose we're given the equation, the relation, minus 6x squared plus 2y is equal to negative 10. Okay, here's the big assumption we're going to make here. We're going to assume that the equation determines a differentiable function f, such that if f of x is substituted for y, then the equation is an identity for every x in the domain of f. Okay, so that's our assumption. We're going to assume there is some function f such that when you substitute it in, it leads to an identity. Okay, so with that assumption, okay, what we're going to do is we're going to differentiate. All right. Okay, so how do we go about doing that? Well, what we're going to do is we're going to differentiate both sides with respect to x. And I'm going to go ahead and switch the y to the notation f of x, just to emphasize that y is a function of x. Okay. All right. So if I differentiate this with respect to x, well, what am I going to get? Well, the derivative of minus 6x squared is what? Minus 12x. The derivative of 2 times f of x. Well, what's the derivative of f? F prime, right? So this is 2 f prime of x is equal to 0. Okay, so this is going to give me minus 12x plus 2 times. Now, if you want, you could switch the f prime to y prime if you want. Okay, and then what I'm going to do is just solve for y prime. So in other words, 2y prime is equal to 12x, so y prime is what? 6x. And that's the derivative. See, we've differentiated implicitly with respect to x. Now, if you were to take this equation and solve for x and differentiate, well, then what would you get, right? It's the same equation up here, right? Okay, here's that equation, right? Well, if I solve for y, I get this equation. Differentiate that with respect to x, what do you get? 6x, see? What do you think? Fun stuff, huh? Not too bad. Now you might be saying, well, why go through all that work? Why not just solve for y and differentiate? It's so much easier. Well, yes, if you can solve for y. What if you can't solve for y? Well, that's why we have implicit differentiation. Make sense? Okay. So let's take a look at our unit circle, right? Here's the equation for our unit circle. So find dy dx, differentiate with respect to x. Now remember, y is a function of x. Okay, I could replace the y with f of x, but I don't have to. Okay, you just have to remember y is a function of x. So if I differentiate, okay, so I want the derivative with respect to x for this whole equation here. Okay, so what am I going to get? I'm going to get 2x plus 2y. Y is a function of x, but now we can't forget the chain rule, right? This is a composition of functions, isn't it? Y squared is a composition of functions. We have the outside function, which is a square function, and then the inside function, which is the y, right? Y is a function of x. See, in other words, just to be a little bit more clear, if I replace the y with this notation, f of x, then here we have the power function, so we bring the 2 down, but then you go inside and differentiate f, right? Which give you f prime. So it's 2y times y prime equal to 0. You see, there you have it. Okay, and now if I solve for y prime, then I'm going to get y prime is equal to what? To minus x all over y. And there you have it. That's the derivative with respect to x? What do you think? Now you might say, well, wait a minute, but the derivative it's written in terms of x and y. Is there any way we can write the derivative in terms of just x only? Well, sure, because I could go back to my equation and I could solve for y, couldn't I? I could do that. So if I go back to my equation and solve for y, well then no problem. Y prime is going to be what? Minus x over the square root of 1 minus x squared. Does that make sense? Right? And of course you have your plus or minus here, right? But does that make sense? Okay, but in a great many of these problems, you can leave it in terms of x and y, and that's not a problem. Okay, let's take a look at this one. Find the slope of the tangent line to the graph of this equation at the point 1 comma negative 2. Okay, well, go ahead and try to solve for y to this, huh? No way. Okay, so let's differentiate both sides with respect to x. So here we're going to have 4y cubed, and then by the chain rule, y prime plus 3y prime minus 12x squared is equal to 5. Okay, there's the calculus, there's the derivative right there. Okay, now what you could do from here, if you want, you could go ahead and just solve for y prime. Or if you want, we can take the 1 and the negative 2 and make your substitution. Okay, it's really entirely up to you. Okay, I'll go ahead and solve for y prime, I guess. So what I'll do is I'll factor out a y prime from each term, like this. And then I'll bring that 12x squared to the right side, and then I'll just divide off. So y prime is equal to 5 plus 12x squared, all divided by 4y cubed plus 3. Okay? And now if I make the substitution, I'm going to take this point and substitute it. Okay, so when I make the substitution, I usually just draw a vertical line like this with the point right down here. It just means I'm ready to substitute. And so then if I do that, I'm going to get 5 plus 12, plug the 1 in for x. And then if I plug a negative 2 in for y, I'm going to get what? Negative 32 plus 3. And so that'll give me negative 17 over 29. Okay, so that's the derivative at the point 1, negative 2. And then all that's left to do is what? All that's left to do is, that's all I want to do, right, was find the slope. Okay, I mean, you could build the equation of the tangent line if you wanted to, but in this example, we just had to find the slope, and there it is. Okay, make sense? Not too bad, huh? Okay. So we're now going to differentiate the inverse trigonometric functions. So here I want to find the derivative of sine inverse of x. So just recall from pre-calculus, by definition, y equal to sine inverse of x means what? It means that x is equal to sine y, right? The double arrow just means, okay, back and forth, right? If you have y equal to sine inverse of x, that means x is equal to sine y. If you have x equal to sine y, that means y is equal to sine inverse of x. Okay, of course, we do have some restrictions. One of the restrictions, of course, is that x is between negative 1 and 1. And then the range of the sine inverse, okay, y is between minus pi over 2 and pi over 2. Okay, just like that. All right, so the reason why we wanted to do this is because here's the thing. We have information about this equation, right? That is, we know how to differentiate it. We already know that, right? Implicit differentiation, right? So if I differentiate both sides with respect to x, then the left side is 1, and then the right side is cosine y times what? Y prime. So in other words, y prime is 1 over cosine y. And so here's my derivative, right? But let's say I want my derivative in terms of x only. Okay, well, I know that cosine squared y is 1 minus sine squared y. So then we know that cosine y is the square root of 1 minus sine squared y. Would you agree with that? Now you might be saying, well, wait a minute, what about the plus or minus? Well, since we're in the interval from minus pi over 2 to pi over 2, cosine is positive. Okay, cosine's positive. Now, what is sine of y? Well, if we look up here, sine of y is x. So then this becomes 1 over the square root of 1 minus x squared. Okay, now we can't let x be plus or minus 1. So we're going to say that the absolute value of x has to be less than 1. Okay, so in other words, the derivative of sine inverse of x is 1 over the square root of 1 minus x squared with the restriction that x is between -1 and 1, and that's the derivative of the sine inverse function. Okay, so I was able to avoid having to use the definition of the derivative. Okay, we just had to rely on some old-fashioned pre-calculus. All right, now you can generate the rest of the inverse trig functions and the same way, and if you do, this is what you'll get. Okay, so here's all the derivatives of our familiar inverse trigonometric functions. Now you do want to commit these to memory. Okay, you do. Okay, it's always best. Okay, especially when you go back to class face to face. Okay, I mean, many instructors won't give you a table or anything like that to look off of, so you definitely want to commit these to memory. All right, so let's take a look at an example here. Let's go ahead and find the derivative to y equal to arctan of the square root of 1 minus x over 1 plus x. Now, if you want, you can rewrite this equation like this. It means the same thing. Whether you write it as arctan or tan inverse of the square root of 1 minus x, 1 plus x, it means the same thing. Okay? All right, so here we go, right? Let's differentiate this. What's the derivative of tan inverse? Well, that's right here. It's 1 over 1 plus x squared, right? Okay, so let's do that. So y prime is 1 over, okay, tan inverse 1 over 1 plus x squared. So 1 over 1 plus x squared, where this is my x right here. But then by the chain rule, I have to do what? Let me switch the colors for you. Now I have to go inside and differentiate this guy. Ah, darn. So that's going to give me what? That's going to give me 1/2, right? 1 minus x over 1 plus x to the negative 1/2 power. And then I got to do what? Let's put this in, I don't know, orange, I guess. Then I got to differentiate this guy and multiply it by that. Oh my gosh, huh? Okay, so how do I do that? Well, we can use the quotient rule. So the derivative of the numerator, which is -1, multiplied by the denominator, subtract off the derivative of the denominator, which is 1, times the numerator, all divided by the denominator squared. Okay, and then of course you can combine like terms, but this is the derivative, right? I mean, it looks rather complex, doesn't it? Yeah, who cares? That's the derivative. You see? Fun stuff, huh? Okay. Fun, fun, fun. Get to work.